let's get started. Can everybody hear me fine without the microphone? Is it okay? All right. But you have to be quiet. So inertia matrix is the inertia matrix, but I always feel I have to talk a little bit more about this because everybody has probably seen what a moment of inertia or a product of inertia looks like, but you kind of have to feel it. Everybody has a feeling when I say mass, right? When I say an airplane has a lot of mass, what does it mean? It means it's heavy, right? It doesn't want to move. It's heavy. You need a lot of power to make it go up in the air. Or if something has a big mass, you need more power. So you have a feeling about mass because it's in our daily lives, but we rarely talk about inertia or moments of inertia, not inertia, but moments of inertia, products of inertia. When I tell you an airplane has a lot of moment of inertia, what does it really mean? Or it has a lot of product of inertia. What does it really mean if a product of inertia is a large number? What does it mean? Right? So it is not really easy it is not in our daily life. So I want to talk a little bit about that. Let's start with the moments of inertia, okay? Second moment of inertia. It's also known as the second moment of inertia, right? So let me write down the formulation. It says this: Ixx is equal to y squared plus z squared dm. This is what you would find if you open up a dynamics book, right? But what does this really mean, right? What does it really mean? And why is there no x? Here are the x's, here is y, and here is z. What does it really mean? Well, it means the following. Let me just try to plot this. Let's say we have an airplane that, say this is the fuselage, and these are the wings, and this is the horizontal tail, and so on and so forth. And let's say this one here is X body. Okay, let's put it here. And let's say this is the CG. And let's say this is Y body. And Z body is into the plane, into the page, of course, right? It is into the page. So what does this say? It says take y squared. So, well, this is all over the body, of course, over the body, over the whole body. So you're going to take an integral for every differential mass. This is a differential mass. Differential mass. So you're going to do this for over the whole body for every differential mass. And y squared and z squared, these are distances, right? So what it says is that take any dm. Let's take this one here. A little differential mass element. Okay? Take this differential mass element. Find y square. Y is the distance, right? Where is the distance? It's this distance here. This is the distance y. This one here. This distance is y. And find the direction, the distance into z. So z is going downwards, right? The z is going downwards. Take the squares plus z squared, the distance square, and add them together, which means this can never be negative. So if I would choose something like this, if I would choose a dm over here, so let's say this is my dm, right? I would be looking at this distance here. This distance, this would be y. And then I would have also into the page a z distance. I would take the square. If I would actually take the square root, I would find that distance, right? I would find the distance onto this axis here. So I'm taking y squared, z squared, and adding it together. I'm taking this dm, I take y squared, z squared downwards, and adding it together. So if I would look from the back, let's say, the airplane would look like this. Okay, let's say this is what the airplane looks like from the back. So again, X now is in the front, coming towards me. So let's say this is my YB and this is my ZB. So am I looking from the front or from the back to this picture? It's from the back, right? I'm looking from the back now. So which means take a little dm, let's take this dm, okay? So I'm looking at the z distance, right? This is z, and this would be y. So this would be the y distance. So I'm taking this as the z distance and the y distance. So I'm adding them all together. So I'm taking the differences between y towards the z-axis, right, towards this axis. And I'm taking the distance again in terms of the z direction, z to the y direction. So I'm looking at this distance. Okay, good. And I'm taking the square, so therefore the moment of inertia will always be positive. Will always be positive. Good. Here's my question to you. What would make, and one more thing, I'm taking the distances, I'm taking the square of the distances, and I'm multiplying them with the little mass element. So this is a differential mass element. It's a small mass element, right? Okay. Here's the question. How can I make Ixx bigger? How can I make Ixx bigger? If I want to make Ixx bigger, if I want to build an airplane that has a large Ixx, what should I do? First of all, I can do a few things. One, tell me one. Mass. I can increase the mass, right? The differential mass element. I can make it a heavier airplane. If I make this airplane out of gold, it would be very heavy. Ixx would be very large because the dm's would, each of the masses would be very large. Each of the dm's would be large. Is that okay? Okay, so you can make it heavier. What else? Bigger dimensions. You can make bigger dimensions. You can make the y bigger, right? Basically, you can make an airplane that looks like that, or not even like this. You can make the airplane like that. And therefore, every dm, if this is x body, would have a large distance to that point, right? Or looking from the back, you could make it like that, so that every point that comes from here, let's say from this dm, that z distance would be large. Okay? So you could really spread out the airplane, both in the z direction and both in the y direction. If you spread out the airplane both in the z direction and the y direction, Ixx will be bigger. And you can make it also heavier. You're spreading out the airplane. Look up here. What does it mean? Spreading out the airplane in y, spreading out the airplane in z. What does it mean? It really means spread out the airplane around the x-axis. Make the airplane bigger around the x-axis. Okay? Make it bigger around the x-axis. So what happens if you make it bigger and bigger? Even if you keep the mass the same, if you make it bigger and bigger around the x-axis, what does it mean? It means the airplane will be harder to turn around the x-axis. Okay? And that's what Ixx is a measure of. It's a measure of how hard it is to rotate the airplane around the x-axis. It's like mass. How difficult is it, when we have mass, we say, how difficult is it to move it, right? That's measure, mass is a measure of that. How difficult is it to move it? With the same force, if the mass is big, you cannot move it too much. The acceleration will be small. If it's a small mass with the same force, you can accelerate it a lot. So mass is a measure of how easy or hard it is to move. Ixx is a measure of how hard it is to rotate the airplane around the x-axis. Because if you spread out the mass, the same mass, if you spread it out, it will be more difficult to rotate. If you don't spread out the mass, but only increase the mass itself, it will still be harder to rotate. If you spread out the mass and make it heavier, it will be very hard to rotate. Okay? So Ixx is a measure of how hard it is to rotate this airplane around its x-axis. So, you probably remember this classic example. Let's say you have a mass like that. Let's call this M1 and M2. Okay? Let's say you have now the same thing with a much bigger mass. Sorry, M1 and M1, of course. And this is with a bigger mass now. This is M2 and M2. And let's say you want to rotate this around this axis here. Okay? And say M2 is much bigger than M1. So which one is harder to rotate? Everybody will say this one is harder to rotate because it's heavier, isn't it? Okay. Now take this one and do the same like that. And again, you want to rotate it around this axis. Okay? So which one is harder to rotate, this one or this one? This one here, right? It's harder to rotate. So which one is harder to rotate, this one or this one? Well, I can't really tell because I don't know which one, if the mass is bigger or if the distance is large enough, I don't know. But if you tell me the inertia, then I know. Because the inertia will be the axis around, I need the inertia around this axis that is pointing into the plane or out of the plane, whatever, this axis. If you tell me the inertia about this axis here and here, I will tell you which one is harder to rotate. So Ixx is a measure of how hard it is to rotate a mass. Now think of it, think of this airplane now. X body is here, look up here. Again, this is X body, right? So if you tell me Ixx for this airplane, I can tell you how hard it is to rotate this airplane around this axis. Okay? If you tell me the mass of this airplane, I will tell you how much force you need to push it. Because I know, for a big mass, you need a lot of force to accelerate. If you tell me Ixx, I will tell you how big your ailerons should be so that you can turn the airplane. Okay? If I want to make this airplane really difficult to turn in this axis, what can I do? I can put a lot of weight on the wingtips. Okay? For example, fuel. I can put fuel on the wingtips. It will be harder to rotate here. Ixx will be quite large. Okay? If you want to make it easy to turn, put all the fuel in the body here. Then it will turn very easy. The mass, the total mass, will be the same. So you still need the same force to push it. But because you're playing with where the masses are, you can change how easy it is to turn in this direction. Does that make sense? Okay. So, how about Iyy? And Izz, products of inertia around the y-axis and the moments of inertia around the y-axis and the z-axis. What are they a measure of? Well, Iyy is a measure of how difficult it is to rotated around its y body axis, IYY. IZZ is a measure of how difficult it is to rotate it around its z-axis. Okay? So if you give me IXX, IYY, IZZ, I can tell you how much moment we need in order to rotate this airplane around its axes. Okay? And that's a measure of, and you can change this doing two things. Changing the mass distribution, leave it far out, or by making the mass bigger. A bigger mass will have higher inertia, and you can see that here, and you can see that in this example. Same distance, bigger mass, more difficult to rotate. Okay? So if you had big masses over here, it would be quite hard to rotate this, right? Is that right? Yeah. Remember the people who are, when they're walking on wires, they have this thing in their hands? I've seen it in a circus, right? In the circus, when they're balancing themselves on the wire, they like to have a big beam like that on their hands. Why do they have it? Well, because it is hard to turn that beam, they can use that beam to balance themselves. Okay? So if you are free with your hands, you might fall very easily, because for you it is easy to rotate. Okay? Because you have a low mass, your mass is very concentrated on the center. For you it is easy to rotate. But if you have a big beam like that, the beam doesn't want to rotate with the weights on the tips. It doesn't want to rotate. So if you're falling this way, you just pull yourself a little bit that way. You're giving a little bit of moment. That thing doesn't want to move, but you are moving a lot because your weight is much smaller. So you can balance yourself. Okay? So, another thing, once you start rotating this, it's hard to stop it too. Okay? It's like a big mass. If you have a big mass that goes very fast, it's hard to stop it. You need a force to stop it, right? A large force. Same thing with this. Once it rotates very fast, it's very hard to stop this. So if you want to have a rotating mass that rotates, you don't want to stop it very easily. You need this. Remember the gyroscopes I was telling you about? They're rotating. The old gyroscopes had heavy wheels that were rotating very fast. And the friction force was not able to stop it very easily. Of course, it would affect it in the long run, but at the beginning it wouldn't affect it too much, because once you have that speed, it is difficult to stop it. How is it difficult? You get a lot of mass, you spread it out a little bit, it's better. Okay? Any questions on the moment of inertia? Understand what this is about? Yes, please.
I heard that, I don't know if it's true or not, but when commercial airplanes, the ground services makes the passengers seats placed according to weight distribution.
Yes.
Is that
of course
important or not?
Of course it is important. We will talk about this in a few weeks. That has something to do with inertia, but it has more something to do with the CG of the airplane. The CG of the airplane should not move too much, for some reasons you will see later in this course. So the passengers are sitting distributed in the airplane so that the CG is always located at a certain point. If the CG moves a little bit too much to the back or too much to the front, it will affect the way the airplane will fly. And we will see that in a few weeks. Okay? But of course that also changes the inertia, how it will rotate, absolutely. Any other questions? Okay, so let's talk about a product of inertia. Now that's a little bit more fun. right here. Just give me a second. Well, let's start with product of inertia then. Let's start with simple one. Let's start with this. I, x, y. Can someone tell me how you would write this in terms of the integral? Do you remember this? Product of inertia. I'm sorry? Can somebody write this for me? How do you write the product of inertia? There's a dm, I tell you that. What's here? Don't tell me nobody knows product of inertia. Somebody can raise their hand and tell me what this should be here. Yes, please. Z plus xz plus yz. If I had a body like this, I had x and y, and I want to find the product of inertia, what would that be? What is it? 2z squared? Where do you get these things? Never heard of this, really. I mean, is there something like that? Huh? X, y, dA. Area. Okay, so dA. Looks a little closer. It's this, xy times dm. That's it. Okay? That's why it's called product of inertia, x times y. So that's an interesting concept. It's x times y times dm. Okay, this is that. So if you had this, if you had I xz, it would be x times z times dm. Okay, and I yz should be equal to y times z times dm. This is again over the whole body, over the whole body. The whole body. So this is wrong. Okay, so let's start with xy, okay? Let's start with xy. I don't even have these. It's no good. Let's see, just give me a second. Oh, it's quite interesting. Okay, well, let's start with this, xy, okay? Let's say I have an airplane like this. And let's say this is x, This is y body. Okay? So let's look at this again. Okay? Let's say you take this little piece here. Let's say you take this little piece here. That's your little dm. Okay? And you want to, let me focus on this a little bit. And you want to find the product of inertia x and y, right? So you take x, would be this distance. This is the x distance. Okay? And then you multiply this with the y distance, which is here. Okay? And then you multiply it with dm, and that would be just one of the particles for dm. And then you do this for all other parts around the airplane. And you add them together, and that will be your xy. If this airplane is symmetric, what do you think xy would be? Why is that? It will be 0, but let me show you why this is. You take the dm on this side of the airplane, right? What do you see suddenly? You see now a minus y. The distance here, it will be this y will be now a minus sign because here is 0. So in this direction, I will have a minus sign. So if this was y here, this would be a minus y. And the x distance, that would be the same, right? So you would have xy dm, and then minus xy times dm. So in the integral up here, these two would cancel out. And that would be true for every particle on the airplane. This one would cancel with this would cancel with that, this would cancel with this would cancel with this, because every time I take something in the y direction, on the other side it will be a minus y. So if you add them together on the integral, they will be 0. So if my airplane has really a symmetry axis like that, then anything I take on this side, on the other side, I will cancel it out because it will be a minus. Why doesn't that happen in moment of inertia? It doesn't happen because you have z squared and y squared, and they are squares, right? It doesn't matter if it goes into minus or plus. So it doesn't happen here. But here it does happen, so it will cancel out. So what can I do to make this one not equal to 0, or make it a number? Because if it is symmetric, I see they will cancel out. So what do I need to do in order to make it not non-zero? Yes?
Using contour surfaces.
Why? How?
I mean, like if you use the on the right side, so we can change the symmetry.
You don't change the symmetry of the airplane if I rotate it. Did it change now? The airplane is the airplane. The airplane is symmetric around this axis, right? Oh, you mean because I moved the surface now it is not symmetric anymore?
Yes.
Okay, yeah, of course. But I was trying to go for something easier. How can you change the IXY on this airplane to be not equal to 0? Make it asymmetric. Okay? So how can you make it asymmetric? You can make one side, listen, you can do two things. You can change the mass property on one side of the airplane. You can make it heavier on this side, then you will have an asymmetry, right? For example, you might do this. Let's say this is X body, and this is Y body. I could put gold on this tip of this wing, right? And now these will not cancel anymore, and suddenly you have a large mass, and now you have a product of inertia. Okay, now you have a product of inertia. You can make it heavier on one side. What else you can do? Even if the mass is the same, you can make it like that. Now, there's an asymmetry, and xy will not be equal to 0, so it will start doing other things. So first of all, okay, let's start here then. Is it good to have ixy 0 on an airplane? I guess so, right? Because then it will be easier to rotate. It will be same to the left, same to the right, so it will be symmetric, it will be nice. So at least ixy, first of all, gives me a measure of symmetry, right? If it's 0, it's a measure of symmetry. Okay. Question to you. Is Iyz also equal to 0, or is it not equal to 0? Iyz. Let's look at Iyz. Iyz. For a symmetric airplane, is it 0 or not 0? Not 0. Why not? Because of tail? What do you mean? What about it? Okay. Let's do our regular thing. Okay? Let's plot this over the body. Let me do this. Let me do that. See, a big body and large wings. So I'm exaggerating this so we can look at it better. This is y, b, and this is zb. Okay? So I take a particle over here. I look at the distance z, I look at the distance y. And then I take another thing on the other side, look at the distance y, and look at the distance z. Would these two cancel? Yeah, but I'm trying to find y and z. Okay, let's make it like that. You mean this? Take a picture over here, dm over here. This is y body, this is z body. So this distance is z. This distance is y. Take the other one on this side, it will be minus y. We are looking at y times z. Am I doing this right, or? So, and z will be this z and that z will be the same. The z directions will be the same. So z times y, z times minus y, so they will cancel if the dm is the same on both sides. Do you understand? So is this one 0 or a number for a symmetric airplane like this? Looks like 0, right? So nothing is as it seems. It is 0, right? For a symmetric airplane, if it's symmetric, because everything on this side will be cancelled on the other side. Right? This one here will be cancelled with this one. You see? Okay. How about the last one, IXZ? Is that one 0 for a symmetric airplane or not? Huh? Not 0. Why not? Now we are a little bit more cautious, right? So is it 0 or not 0? Not 0. Some people say 0. Okay, let's see. Let's plot the airplane from the side so I can plot this thing. This is X body. This is Z body, right? Okay. So X and Z. take one particle over here, dm, take x, and take z. Okay, these are the distances. Is there an equivalent particle on this side? Not necessarily, right? Is it an equivalent particle on that side? No, not necessarily. So not necessarily do I have an equivalent for this dm to be cancelled. Okay? So a result, for most airplanes, this is not equal to 0 for most airplanes. Can you make an approximation that's saying that this dm, well, there's something that is similar to that. There's something that's similar over here. This one, well, the tail, of course, not really similar, but maybe this will cancel that one. Maybe this will cancel that, and this will cancel that. So on the long run, you know, you can make an approximation equal to 0. Can you make that approximation? Sometimes you can, because it is not a large number, you see. If the airplane would be looking something like this, a weird shape like that, for this mass, you probably cannot make that approximation because there's a large mass over here and there's nothing on this side. So this will be a large number. But for something that is quite slender like this, and there's a little bit of offsets here, this number is not too big for most airplanes. Okay? Understand that? So you could make it 0. You could take it 0, but it's not really 0. Okay. So here is then the other question now. So what does it now mean then? If I have products of inertia, what does it really mean? It means, first of all, if it's not 0, it means there's some sort of an asymmetry, right? If it's 0, it's nice, then it means there's an axis around which everything is smooth and 0. Okay? Let's say x, z, z. Let's say this airplane is symmetric, has a symmetry plane, and around the x-axis, right, in this direction, I have sort of a symmetry everywhere. All right? Let's say I have a symmetry like that. What happens if I would put a very large mass on this horizontal tail's tip here, and I try to rotate it around the x-axis again? So let's say this is the horizontal tail and this is the wing. Just to make it obvious, okay, let's say I put a very large mass over here. This part is out of gold. Okay, and this is the CG now. And let's say I'm trying to rotate this around the x-axis. What will it do? Now, if I try to rotate it, what will it do? Without the mass, let me just stand up here. Without the mass, if I rotate this around the x-axis, the airplane would make a nice rotation, right? It would make a nice rotation like that. If I had a large mass on the tail, on the horizontal tail, if I tried to rotate it, it would probably try to do something like that. Because this part doesn't want to move. Now it has a lot of inertia. The other part wants to move. So it will not be a smooth rotation. If I give a poor rotation like this, a pure moment like that, it will not be a pure moment. It will more like be something like that. There will be motions, I mean there will be rotations in other axes as well, although I give only a moment in the x-axis. If this thing is totally symmetric and I give a moment in the x-axis, it will make a perfect turn in the x-axis. Okay? If the mass distribution is not symmetric, meaning that let's say one of these wings or one of these engines are very heavy, let's say, if I give an x rotation like that in space, the airplane will not only make an x-axis rotation, it will rotate in other axes as well. Okay? Does that make sense? I mean, I'm just trying to, I hope that you can relate it to your daily life. If I would put a very heavy stone over here and I would try to, or here somewhere, so make it asymmetric, and I try to rotate it in one direction, it will not rotate perfectly in the x direction. It will do something like that. Okay? So that effect is what what is caused by this product of inertia. Basically a measure of asymmetry in the whole system. If there's an effect of asymmetry, one rotation in one axis will not give you a perfect rotation in space anymore. It will give you something else, okay, because of this asymmetry. And that is true for all axes. If I want to give a pitch axis, okay, and I have an asymmetry in one of these axes in the system, okay, the airplane, if I just give a roll axis, it might actually be doing this. Okay. Let's say I put a large mass on the wingtip, on this one here, on the left-hand side. For you, it's the right? Here. If I put a large mass on this side, and I'm trying to make it a pitch up. If the axis is here, and I'm trying to make it a pitch up, because of this heavy wing, it will try to do this, right? Although I give this, it will do that. But if it was perfectly symmetric, or there was no product of inertia, it would be just doing that, right? But if this wing is heavy, it might be doing this. So a product of inertia, from a practical standpoint, really means that. Which means if you want to pitch up this aircraft, you don't only need that. If the product of inertia is not equal to 0, you might need other moments as well. Because if you just give that, and if the product of inertia is not equal to 0, you might actually see something like this, which means you need to counteract for that on that axis as well. Okay? So that's what a product of inertia really tells you. If the product of inertia is equal to 0, it means there is a principal axis, which means, in fact, in this case, we have two product of inertias equal to 0 for this airplane, which means there's actually a symmetry plane. Because we have a symmetry plane, two of the product of inertias are equal to 0. As a result, I give an a pitch moment, and it will give you a perfect pitch. You give you a roll moment, it will give you a perfect roll. And it will give you a perfect, now what this one I'm not so sure anymore, around the z-axis, because xz is not equal to 0. Okay? But if it was perfectly symmetric, then you could be doing this, we could be doing this. If it's not symmetric, let's say all fuel is gone over here, and you have a lot of fuel over here. You do this, the airplane would be doing this, and the product of inertia would not be equal to 0. So that's what the measure, that's what product of inertia measures for us. So moment of inertia is how difficult it is to rotate it in one direction. Product of inertia gives you information about how the mass is distributed in terms of symmetry, asymmetry. If I give in one direction, one axis, one input, what's going to happen to the whole airplane? Does that make sense? Okay. So, that's it, inertia matrix. It tells you everything about the airplane's rotational behavior. How heavy, how much moment you need to rotate it. How difficult it is to rotate. If I try to rotate it in one direction, will it also rotate in all other directions? It's all the property of how the mass is distributed on this rigid body. How is the mass distributed? It's not a point anymore. See, the point mass of Newton's law was only one point. Now we are talking, how is the mass distributed? If the mass is distributed spread out, it's difficult to rotate. If it's asymmetric, the rotation on this axis will cause rotations in other axes as well. It's a property of this mass, of this rigid body. Okay? So, any questions? All right. Here's my question. Do the inertias depend on the axis system that I choose? The numbers will be different, right? If I choose a different axis coordinate system, it will change. For example, take this one. If I move the axis coordinate system somewhere here, let's say I move it from here, let's say I move it like that. Although the vehicle is the same vehicle, the numbers in the inertia matrix will change, right? Because now I will look at this y, this x, you know. In fact, some of the product of inertias now are not zero anymore. But then it means, what happens if I rotate this airplane around this axis, around this x-axis? Will it only rotate around the x-axis? Now there's an asymmetry. The product of inertias are not equal to zero anymore, right? If I try to rotate around xp, it will just rotate like that, because there's no symmetry anymore. So I put the x body in the symmetry axis for a reason. It makes things easier for me. You know, when I defined the body fixed coordinate system, I said x body is towards the node, z body is in the symmetry axis, y body to the side. Why do I put it in the symmetry axis? I put it in the symmetry axis so that some of the product inertias are actually zero or close to zero. I could have chosen a coordinate system like that for the airplane, but the inertia matrix would be quite difficult. It would have a lot of moments of inertia. It would have numbers according to this coordinate system. For example, Ixx for this coordinate system is quite different from this Ixx, right? One is how difficult it is to rotate the airplane around its x-axis. This coordinate system would tell me, Ixx for this coordinate, how difficult is it to rotate this airplane around this axis, this axis, right? So they would be totally different. Therefore, the moment of inertias and product of inertias, basically in total we call it the inertia matrix, depends on the coordinate system I choose. Okay? And since we are writing everything in the body fixed coordinate system, we are writing this also in the body fixed coordinate system in this problem. It doesn't have to be. As the coordinate system is changing for the aircraft, although the aircraft is not changing the mass properties, the numbers in the inertia matrix would change. So, do you think we know all inertias or the inertia matrix for every airplane? Well, if you build an airplane, you should know it, right? Because then you should know how difficult it is to rotate if there's an asymmetry and things like that. Now, this is how you calculate the inertia, though. You take a little differential mass and then multiply the distances, take the differential mass and integrate over the whole body. Now imagine an airplane with all the avionics, passengers, seats, hydraulics, engines, fuel, structure. Shouldn't be very easy to calculate it, isn't it? Okay, believe me, it's not easy. Okay, there are a few ways you can do it experimentally, which means you take that airplane, you actually give a moment and see how much it turns, and then you can go back and calculate Ixx. But setting up a test rig for this like that is not easy, right? You cannot put an airplane in space and someone just rotates it like I do. Unless you have Superman somewhere when he tells you how much moment he puts on. Another way is to put this into a computer, right? Into a CAD program, into a computer drawing, right? If you put this into a CAD program, if you draw everything, but you have to draw now everything, like every avionics, hydraulics, the mass properties, the material, everything goes into the computer. The computer can, of course, do that calculation for you. It can take the integral over the whole body and tell you the inertia for this whole airplane, okay? But then again, you change an avionics system, you change the fuel. The fuel is changing, of course, the inertia properties, right? Or you have passengers all moving to the back or running to the front. It will change the inertia as well, right? So the inertia will keep changing a little bit. So what we usually do is we calculate an inertia for an airplane. And when we have a good number, we are very happy, because it's not easy to calculate inertia for airplanes because there's so much stuff inside, okay? I'm talking, of course, about accurate inertias. If the inertias are, if you want to have an approximate inertia, you can always guess a number. And we know what the inertia for an airplane like this is, or the inertia matrix looks like. Okay? Any questions? Okay, it's time to give a break. And then we are going to write the rotational dynamics in the next hour.